In a properly designed electrical system, a main fuse or circuit breaker provides overcurrent protection for the entire panel or circuit, while branch breakers provide protection for individual branch circuits. If a short circuit occurs between grounded and ungrounded conductors, it will create a high fault current. This current will flow through all available paths, including the main fuse and the branch breakers. The main fuse is typically rated for a higher current capacity than the branch breakers. This means that it will take longer for the main fuse to open than the branch breakers. The branch breakers are designed to trip quickly when an overcurrent condition occurs. However, if the fault current is extremely high, the branch breakers may not be able to trip fast enough to prevent damage to the conductors. In this case, the main fuse may have opened first for the following reasons. Firstly, the short circuit created a very high fault current that exceeded the trip rating of the branch breakers. Secondly, the branch breakers may have been defective or improperly installed, causing them to fail to trip when needed. Thirdly, the branch breakers may have been rated for a current that was too high for the conductors they were protecting. It's unusual for a main fuse to open before branch breakers, but it is possible in cases of extreme fault currents or faulty branch breakers. The use of Class T fuses as main protection is also not recommended for modern electrical systems. Modern fuses or circuit breakers with time current curves specifically designed for MC cable protection should be used instead. To elaborate further, let's delve deeper into the concepts and potential causes. When a short circuit occurs, the impedance of the circuit drops dramatically. This results in a surge of current that can be many times the normal operating current. This high fault current places significant stress on all the overcurrent protection devices in the circuit, including both the main fuse and the branch circuit breakers. The speed at which an overcurrent protection device operates, whether it's a fuse or a circuit breaker, is determined by its time current characteristic curve. This curve illustrates the relationship between the magnitude of the overcurrent and the time it takes for the device to trip or blow. Fuses typically have an inverse time current characteristic, meaning that the higher the current, the faster the fuse will open. Circuit breakers also have time current characteristics, but they can be more complex with instantaneous trip elements and time delay elements. The instantaneous trip element is designed to trip the breaker very quickly in response to a high fault current, while the time delay element allows the breaker to ride through temporary overloads. The coordination between the main fuse and the branch circuit breakers is crucial for ensuring proper overcurrent protection. Ideally, the branch circuit breakers should trip before the main fuse in the event of a fault on a branch circuit. This prevents the entire panel from being shut down and isolates the fault at the affected circuit. However, if the fault current is high enough, or if the branch circuit breakers are not functioning correctly, the main fuse may open first. Several factors can contribute to a main fuse opening before the branch circuit breakers. Firstly, the magnitude of the fault current is a critical factor. If the fault current is significantly higher than the trip ratings of the branch circuit breakers, the main fuse may open very quickly before the breakers have a chance to trip. Secondly, the time current characteristics of the main fuse and the branch circuit breakers play a crucial role. If the main fuse has a faster time current characteristic than the branch circuit breakers at high fault currents, it may open first. Thirdly, the condition of the branch circuit breakers is important. If the breakers are defective, improperly installed, or have been subjected to repeated overloads, they may not trip as quickly as they should, increasing the likelihood of the main fuse opening first. Fourthly, the ampacity of the conductors in the branch circuits must be properly matched to the rating of the branch circuit breakers. If the breakers are rated too high for the conductors, they may not provide adequate protection against overcurrents, and the main fuse may open to protect the conductors. It is essential to investigate the cause of the main fuse opening before simply replacing it. A thorough inspection of the branch circuit breakers, the wiring, and the connected loads should be performed to identify any potential problems. The branch circuit breakers should be tested to ensure that they are tripping correctly at their rated current. The wiring should be checked for any signs of damage or deterioration. The connected loads should be examined to ensure that they are not drawing excessive current. If any problems are found, they should be corrected before the main fuse is replaced. In addition to addressing the immediate cause of the main fuse opening, It is also important to consider the overall design and coordination of the electrical system. The main fuse and the branch circuit breaker should be properly sized and coordinated to ensure that they provide adequate overcurrent protection for all parts of the system. The use of Class T fuses as main protection is generally not recommended for modern electrical systems. Class T fuses are current-limiting fuses that are designed to provide very fast overcurrent protection. However, they can be more expensive than other types of fuses, and they may not be compatible with all types of electrical equipment. Modern fuses are circuit breakers with time current curves specifically designed for metal-clad cable protection should be used instead. These devices are designed to provide adequate overcurrent protection for metal-clad cable while also being compatible with a wide range of electrical equipment. Moreover, proper installation practices are paramount in ensuring the safety and reliability of an electrical system. All wiring connections must be made securely and in accordance with the National Electrical Code, or NEC. Overcurrent protection devices must be properly sized and installed to provide adequate protection against overloads and short circuits. Regular maintenance and inspection of the electrical system are also essential for identifying and correcting any potential problems before they can lead to a main fuse opening or other electrical hazards. Specifically, referring to the NEC, there are several articles that pertain to overcurrent protection and fuse selection. Article 240 provides general requirements for overcurrent protection, including the selection and coordination of overcurrent devices. Article 310 covers conductor ampacity, which is essential for determining the appropriate size of overcurrent protection devices. Article 430 covers motor circuits, which have specific overcurrent protection requirements. When selecting fuses or circuit breakers, it is important to consider the following factors. Firstly, the interrupting rating of the device must be sufficient to handle the available fault current at the point of installation. Secondly, the voltage rating of the device must be compatible with the system voltage. Thirdly, the current rating of the device must be appropriate for the ampacity of the conductors being protected. Fourthly, the tan current characteristic of the device must be coordinated with other overcurrent protection devices in the system. It is always best to consult with a qualified electrical engineer or electrician when designing or modifying an electrical system. They can help ensure that the system is safe, reliable, and in compliance with all applicable codes and standards. In the described scenario, the fact that the time clock and spring wound timer are wired in parallel means that they both draw current from the same circuit. This can increase the overall load on the circuit and potentially contribute to an overload condition. The use of metal-clad cable as the wiring method is generally a good practice, as metal-clad cable provides a high degree of protection against physical damage and electrical faults. However, it is important to ensure that the metal-clad cable is properly installed and grounded. If the metal-clad cable is not properly grounded, it can become a source of electrical shock. In conclusion, while it is unusual for a main fuse to open before branch breakers, it is possible in cases of extreme fault currents or faulty branch breakers. A thorough investigation of the electrical system should be performed to identify the cause of the problem and to ensure that the system is safe and reliable. It's also crucial to consider the overall design and coordination of the electrical system. The main fuse and the branch circuit breakers should be properly sized and coordinated to ensure that they provide adequate overcurrent protection for all parts of the system. The use of Class T fuses as main protection may not be the best choice for modern electrical systems, and modern fuses or circuit breakers with time current curves specifically designed for metal-clad cable protection should be considered instead. Regular maintenance and inspection of the electrical system are also essential for identifying and correcting any potential problems before they can lead to a main fuse opening or other electrical hazards. Let's now consider the scenario with some actual numbers as an example. Imagine a panel with a 200 amp main fuse protecting a 120/208 volt system. Suppose there are two branch circuits, each protected by a 20 amp circuit breaker, feeding separate 120 volt loads. The branch circuits are wired with number 12 American wire gauge, or OG, copper conductors, which have an ampacity of 20 amps according to NEC table 310.15b16. Now, let's say a short circuit occurs on one of the branch circuits, resulting in a fault current of 2000 amps. This is a substantial fault current, far exceeding the ratings of both the branch circuit breaker and the main fuse. The 20 amp branch circuit breaker is designed to trip quickly in response to an overcurrent. However, with a fault current of 2000 amps, the breaker may not be able to trip instantaneously. It might take a few milliseconds for the breaker to interrupt the circuit. During that time, the 2000 amps fault current is flowing through both the branch circuit breaker and the main fuse. The 200 amp main fuse is also designed to protect against overcurrents, but it has a higher current rating than the branch circuit breaker. This means that it will take longer for the main fuse to open than the branch circuit breaker. If the branch circuit breaker fails to trip quickly enough, the 2000 amps fault current could cause the main fuse to open before the branch circuit breaker. This is because the main fuse is subjected to a higher level of stress for a longer period of time. In this scenario, several factors could contribute to the main fuse opening. Firstly, the magnitude of the fault current is very high, exceeding the interrupting rating of the branch circuit breaker. Secondly, the branch circuit breaker may be slow to trip due to its design or condition. Thirdly, the main fuse may have a faster time current characteristic than the branch circuit breaker at high fault currents. To prevent this from happening, it is important to ensure that the branch circuit breakers are properly sized and coordinated with the main fuse. The branch circuit breakers should have an interrupting rating that is sufficient to handle the available fault current at the point of installation. They should also be tested regularly to ensure that they are tripping correctly at their rated current. The main fuse should be selected with a time current characteristic that is coordinated with the branch circuit breakers. This means that the main fuse should not open before the branch circuit breakers in the event of a fault on a branch circuit. In addition, it is important to ensure that the wiring in the branch circuits is properly sized and installed. The conductors should have an ampacity that is sufficient to carry the load current without overheating. The connection should be made securely and in accordance with the NEC. Also, the 120 volts loads that are wired in parallel should be evaluated so the appropriate fuse and breaker sizes are installed. If the loads draw too many amps when running in parallel, the fuse and or breaker will likely trip as expected. In summary, the coordination of overcurrent protection devices is crucial for ensuring the safety and reliability of an electrical system. The main fuse and the branch circuit breaker should be properly sized and coordinated to protect against both overloads and short circuits. Regular maintenance and inspection of the electrical system are also essential for identifying and correcting any potential problems before they can lead to a main fuse opening or other electrical hazards. Finally, it is very important to be aware of arc flash risks and adhere to the appropriate personal protective equipment standards and guidelines.